Chapter 1 Real Numbers. Real numbers include rational and irrational numbers. Rational means the number which we can write in the form p by q, where p and q are integers and q not equal to 0. Irrational numbers means the number which we cannot write in the form p by q, where p and q are integers and q not equal to 0. In this chapter, the first section is Euclid's division lemma. Statement. The statement is this: given positive integers a and b, there exist unique integers q and r satisfying a is equal to bq plus r, where 0 less than or equal to r less than b. Statement is, given two positive integers a and b, there exist two integers p and q satisfying a is equal to bq plus r, where 0 less than or equal to r less than b. The first question is exercise 1.1. First question, find the HCF of 135 and 225 using division algorithm. I have written algorithm here. Algorithm is a well-defined steps which we are using to do or solve a problem. So, algorithm is the well-defined steps which we are following to solve a problem. So, here lemma. Lemma is the proven statement which we can use for proving another statement. Lemma is a proven statement which we can use for proving another statement. So, these are algorithm is the steps. So, we are using this as steps to find HCF of 135 and 225. So, here 225 is greater than 135. Write 225 in terms of 135. For this, divide 225 divided by 135 one time 135. So, it is remainder is 90. Remainder is 90. So, we can write 225 as 135 into 1 plus 90. 135 into 1 plus 90. Next, we have to write 135 in terms of 90. So, 135 divided by 90. 1 time 90. So, it is 45. So, we can write 135 as 90 into 1 plus 45. Next is, you should write 90 in terms of 45. 45 into 2 is 90 and remainder 0. So, we can stop here. We have to get the remainder as 0. Then, the last divisor is the HCF. So, HCF is equal to HCF of 135 225 is equal to 45. Find the HCF of 135 and 225 using division algorithm. So, 225 is greater than 135 and we are writing 225 in terms of 135 as 135 into 1 plus 90. And then write 135 in terms of 90. So, 135 is equal to 90 into 1 plus 45. Then write 90 in terms of 45. 45 into 2 is 90 plus 0. So, remainder is 0. When you get the remainder, you can stop. So, HCF is the last divisor. Next is HCF of 4052 and 12576. 12,576 is greater than 4,052. So, write 12,576 in terms of 4,052. So divide this. 12,576 divided by 4,052. How many times it is? 3 times. So it is 12,156 and the balance is 420. So we can write this as 4,052 into 3 plus 420. Next, 4,052 is greater than 420, right? 4,052 in terms of 420. In terms of 420. So, (4,052) divided by 420. How many times it is? 9 times. So, you are getting this as 3,780. So, the remainder is 272. So, you can write this as 420 into 9 plus 272. Then you have to write 420 in terms of 272. So, 420 divided by 272. 420 divided by 272. So, one time 272 and when you subtract you will get this 148. So, you can write this as 272 into 1 plus 148. Then 272 is greater, write 272 in terms of 148. So, 272 divided by 148. One time 148, subtraction 124 is a remainder. So, you can write this as 148 into 1 plus 124. Then divide 148. Write 148 in terms of 124. (148) divided by 124. One time 124, 24. So, you can write this as 124 into 1 plus 24. Then you have to write 124 in terms of 24. So, 124 divided by 24, 5, 120. So, 4 is a remainder. So, you can write 124 is equal to 24 into 5 plus 4. Next, write 24 in terms of 4. So, 4 into 6 plus 0. So, the remainder is 0. So, we can write this as HCF is equal, HCF of 4,052, 12,576 is equal to the last divisor. Last divisor is 4, is equal to 4. So, 12,576 is greater than 4,052. So, we can write 12,576 is equal to 4,052 into 3 plus 420. Then 4,052 is equal to 420 into 9 plus 272. Then 420 is equal to 272 into 1 plus 148. Then 272 is equal to 148 into 1 plus 124. Then 148 is equal to 124 into 1 plus 24. Then 124 is equal to 24 into 5 plus 4. 24 is equal to 4 into 6 plus 0. So, the last divisor is 4. So, that is the HCF. Next is exercise 1.1 third question. An army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? So, maximum number of columns clearly means HCF. HCF of 616 and 32. HCF of 616 and 32. So, first we should divide. 616 is greater than 32. So, we can write 616 in terms of 32. $288. So, 8 is the remainder. So, you can write 616 as 32 into 19 plus 8. Next is 32 is greater. So, 32 is equal to, you have to write 32 in terms of 8. 8 fours are plus 0. So, the HCF of 616 and 32, that is the maximum number of columns, that is equal to, the last divisor is 8. Next question, example 2. Show that every positive integer is of the form 2q and that every positive odd integer is of the form 2q plus 1 where q is some integer. Even integer is 2q and odd integer is 2q plus 1. So, positive even integer. So, let a be a positive integer. So, using Euclid's division lemma, we can write a is equal to bq plus r where 0 less than or equal to r less than b. Let b is equal to 2. A is equal to 2q plus r where 0 less than or equal to r less than 2. 0 less than or equal to r less than 2 means r can take values 0 and 1. Therefore, r can take values 0 and 1. So, two cases. First is case 1 when r is equal to 0. When r is equal to 0, a is equal to 2q, it is clearly even. Case 2, when r is equal to 1, a is equal to, r is equal to 1, it is a is equal to 2q plus 1, clearly odd. So, what we can say is every positive even integer is of the form 2q and every positive odd integer is of the form 2q plus 1. So, we have started from a be a positive integer, and using Euclid's division lemma we can write a is equal to bq plus r where 0 less than or equal to r less than b. Let b is equal to 2, so a is equal to 2q plus r, 0 less than or equal to r less than 2. Therefore, r can take values 0 and 1. Case 1, when r is equal to 0, a is equal to 2q, it is clearly an even number. And case 2, r is equal to 1, a is equal to 2q plus 1, it is odd. So, what we can say is every positive even integer is of the form 2q and odd integer is of the form 2q plus 1. Next is exercise 1.1 fourth question. Use Euclid's division lemma to show that square of any positive integer is of the form 3m or 3m plus 1 for some integer m. The square of any positive integer is of the form 3m or 3m plus 1. So, we did a positive integer. Let a be a positive integer. So, using Euclid's division lemma, we can write a is equal to bq plus r where 0 less than or equal to r less than b, and let b is equal to 3. So, we can write a is equal to 3q plus r where 0 less than or equal to r less than 3. Therefore, r can take values 0, 1 and 2. Therefore, r can take values 0, 1 and 2. So, case 1, when r is equal to 0, when r is equal to 0, a is equal to 3q. What we need is square of any positive integer. So, a square is equal to 3q whole square, which we can write as 9q square. But we need this in terms of 3. So, we are writing 3 into 3q square, which is equal to 3m, where m is equal to 3q square. So, first we have given a, b as 3. So, r can take values 0, 1 and 2. So, case 1 is when r is equal to 0. When r is equal to 0, a is equal to 3q. So, a square is 3q whole square, which we can write as 9q square, which is 3 into 3q square, which is equal to 3m, where m is equal to 3q square. Case 2, when r is equal to 1. When r is equal to 1, we can write a as 3q plus 1. So, a square is equal to 3q plus 1 whole square. This is of the form a plus b whole square. So, a square 3q whole square plus 2 into 3q into 1 plus b square. So, we can write this as 9q square plus 6q plus 1. 9q square plus 6q plus 1. Take 3 out. So, it is 3 into 3q square plus 2q plus 1, which is equal to 3m plus 1, where m is equal to 3q square plus 2q. So, case 2, when r is equal to 1, we can write a as 3q plus 1. So, a square is 3q plus 1 whole square. This is of the form a plus b whole square. So, a square plus 2ab plus b square. So, finally, we got 9q square plus 6q plus 1. Then I have taken 3 out. So, 3 into 3q square plus 2q plus 1. This is equal to 3m plus 1, where m is equal to 3q square plus 2q. Next is when case 3, when r is equal to 2. Case 3, when r is equal to 2. So, a is equal to 3q plus 2. So, a square is equal to 3q plus 2 whole square. This is of the form a plus b whole square, 3q whole square, a square plus 2 into a into b plus b square. So, it is equal to 9q square plus 12q plus 4. I am writing 4 as 3 plus 1. So, this is equal to 9q square plus 12q plus 3 plus 1. From the first 3 terms, I am taking 3 out. So, 3 into 3q square plus 4q plus 1 plus 1. So, this is equal to this is equal to 3m plus 1, where m is equal to 3q square plus 4q plus 1. So, first is 3m, second is 3m plus 1 and the last is also 3m plus 1. So, every square can be written as 3m or 3m plus 1. Next is exercise 1.1, fifth question. Use Euclid's division lemma to show that cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. So, we need an integer, let a be an integer. So, using Euclid's division lemma, we can write a is equal to bq plus r, where 0 less than or equal to r less than b. Take b as 3. So, it is a is equal to 3q plus r, where 0 less than or equal to r less than 3. So, r can take values 0, 1 and 2. So, case 1, when r is equal to 0. When r is equal to 0, a is equal to 3 cube. So, cube, a cube is equal to 3q whole cube, which we can write as 27q cube. But here we need 9m, 9m plus 1 or 9m plus 8. So, we can write this as 9 into 3q cube, 9 into 3q cube, which we can write as 9m, where m is equal to 3q cube. So, we are proving cube of a positive integer. So, a is equal to 3q, a cube is equal to 3q whole cube. It is equal to 27q cube is equal to 9 into 3q cube, which we can write as 9m, where m is equal to 3q cube. Next is case 2, when r is equal to 1. When r is equal to 1, a is equal to 3q plus 1. So, a cube is equal to 3q plus 1 whole cube. This is of the form a plus b whole cube. So, first term is a cube. So, a cube plus 3a square b plus 3a b square plus b cube. So, this is equal to 27q cube plus 27q square plus 9q plus 1. From first 3 terms, we can take out 9. So, it is 9 into 3q cube plus 3q square plus q plus 1, which is equal to 9m plus 1, where m is equal to 3q cube plus 3q square plus q. Case 2, r is equal to 1. So, a is equal to 3 cube plus 1. A cube is equal to 3 cube plus 1 whole cube. So, this is of the form a plus b whole cube. So, a plus b whole cube is equal to a cube plus 3a square b plus 3ab square plus b cube. Applying that, we are getting this as 27q cube plus 27q square plus 9q plus 1. From the first three terms, we are taking 9 out. So, 9 into 3q cube plus 3q square plus q plus 1. So, it is equal to 9m plus 1, where m is equal to 3q cube plus 3q square plus q. Then case 3. Case 3, when r is equal to 2. When r is equal to 2, a is equal to 3q plus 2. So, a cube is equal to 3q plus 2 whole cube. This is again of the form a plus b whole cube. So, a cube plus 3a square b plus 3ab square plus b cube. So, this is equal to 27q cube plus 54q square plus 36q plus 8. So, from these three we can take 9 out. 9 into 3q cube plus 6q square plus 4q, then plus 8. So, this is equal to 9m plus 8, where m is equal to 3q cube plus 6q square plus 4q. So, what we got is cube of any positive integer is the form 9m, 9m plus 1 or 9m plus 8. Homework exercise 1.1, first question 2, 3. First question subdivisions 2 and 3 and second question.